So we were discussing how to make an effective current mirror. When we say effective, what I essentially mean is something which will be able to copy the current from one branch to another accurately, and also it will be insensitive to voltage swing across the devices, right? So this is what we were discussing. Okay, so and while we were towards the end of yesterday's lecture, the part that I alluded to was, I mean, if you choose the devices M0, M1 to be identical, M0A and M2 to be identical, then it seems like as long as M1 and M2 are in saturation, it seems like the output resistance looking from here is of the order of approximately the intrinsic gain of M2 times RDS of M1, right? So this is kind of one order of magnitude higher than only RDS. So this is certainly a better current source across the terminals V0 and ground, simply because it gives you a better, a higher output resistance. Also, the second part is this is a more accurate current mirror than if you only had M0 and M1 and M0 and M1 and V0 was connected directly here, right? So this is a more accurate current mirror with respect to this structure. Right? Simply because in this case, if V0 goes up and down, then naturally the entire V0, the entire change of V0 falls across this device. But in the structure on the left, if this voltage V0 goes up and down, then only a small fraction of that voltage of that change is reflected across the device M1, and hence you have much smaller dependence of current on changes in V0. So that is point number one. And point number two is, in this case, naturally, if you can ensure that these two, the drain voltages of M0 and M1 are identical, regardless of whatever V0 change, whatever change in V0 the structure might experience, then it makes sense. The conclusion should be obvious that the mirroring of current from the left branch to the right branch to the right branch in this structure is better than this structure, simply because these two nodes kind of are always at similar voltages if biased properly. Now, this if biased properly is a designer's job, and that's what we were discussing when we stopped, right? And the stuff that we were discussing was that what is the, I mean, if the structure on the left is always better than the structure on the right, then under any circumstance can we use the structure on the left? The answer to that was no, simply because here on the structure on the right, the minimum V0 that it can experience is VGS minus 1 threshold voltage, VGS of 1 and minus 1 threshold voltage, which is essentially 1 V overdrive. So from our previous discussions, we know that V overdrive can be as low as 100 millivolt. So if you are operating with a voltage supply, right, of let's say 1 volt, you are only expending 10% of the voltage supply to bias, right? So that's not too much, one might argue. But in the circuit on the left, if we do the same thing, so what do we see? So let's say the typical threshold voltages are of the order of 500 millivolts. So this effectively becomes 600, or let me just write out the expressions. This is VGS1 or VGS0, they are the same thing, plus, not plus, VGS0. So this voltage becomes VGS naught plus VGS of not A, right? So naturally this voltage becomes the minimum voltage that M2 will experience becomes VGS, or M2 can sustain, becomes this minus 1 threshold voltage of M2. And to the first order, if we assume that all the VGS are identical, right? So then effectively this becomes 2 VGS minus threshold voltage, which is essentially 1 VGS is, since a VGS is threshold voltage plus overdrive, so this becomes 1 threshold voltage plus 2 OV overdrive. So this is approximately what this, let's say this is 0.5 and that those two are 100 millivolts. So this becomes 0.7 volts, right? So now we can easily imagine that if you're operating with a supply of 1 volt and you spend 70% of the supply to bias just a current source, then you are basically left with nothing, right? To supply whatever circuit might be attached to V0, right? So naturally, I mean, these type of architectures have lost its value as the voltage supply has scaled down over the years. So when there was a time when analog circuit designers used to use these structures when the typical VDD used to be 5 volt or higher, right? In that case, 0.7 out of 5 is okay, or maybe even 1 volt out of 5 is 25% loss. That is fine. But when the voltage supply has scaled down and threshold voltage hasn't scaled down as much, so these type of structures become a problem. So then obviously the need for searching for more type of architectures arose. And that is one such architecture that I will try to motivate next. Okay, so now we want cascade. So we don't want to get rid of cascade, which means this structure has to be there. This is V0. This I don't want to compromise on. And we want mirroring, which means the current source has to be connected to something here. That is also kind of given. So now, if voltage supply, if the minimum V0 is the issue, right? So let me first ask you. I should not put the bubble here. It might seem like this is a EMOS. So let me first ask you. Let's say I am able to bias this with some VB2, let's say VB1. I can free to choose VB1 and VB2. What is the minimum V0 that you can sustain while keeping both M1 and M2 in saturation? I'm asking for V0 min. In terms of V overdrive, threshold voltage, VGS. What will you think? I mean, how will you approach this?
Find out the sheet one like between that M1 and M2, the minimum value of
okay, fine. What is the minimum value? Right. So VB1 minus VT. So effectively 1 overdrive. Right. So this has to be 1 overdrive. I'm assuming overdrives are same for M1 and M2. Right. Just to simplify calculations. Okay, fine. So this we got the minimum here. Then So VB2 will be, for this value of V over drive, what should be VB2? Right. So this has to be one threshold voltage plus V over drive over the source voltage, right? So 2 V over drive essentially then. Right? So essentially VGS, this plus VGS. VGS is one threshold voltage plus 1 V over drive. I'm adding it to V over drive. So what is V naught mean? Right? 2 V over drive, right? So this becomes 2 V over drive. So 2 V over drive, we can, this is approximately 100 millivolt, 200 millivolt. So this is much better than 700 millivolt, right? So you are, if you are working with 1 volt supply in the earlier architecture, in this architecture, you would have to leave out 700 millivolts of headroom in a 1 volt supply, which would have been wasteful. But in this architecture, if you can make this architecture, then the minimum V naught is 200 millivolt, which is only 20% of the supply, right? So then that it makes a lot of sense to investigate how do I generate this VB1 and VB2 so that I can use this type of architectures. Okay, so that's good. So let's figure out how to go about doing it. So let's say that for the time being, and by the way, I want mirroring, I want cascode. So this should be there. This has to be there. Just that I have to figure out how to generate these voltages. I need to find out how to generate this voltage, such that the conditions of this structure gets met. Right? Okay, fine. So I know that this voltage can go to as low as 1 V over drive. And assume all the V over drives and threshold voltages are identical, just so that gives you a ballpark estimate. Okay, so if this goes here now what we should the way we should think about it is, if this voltage is minimum voltage has to be V over drive, and I also want accurate mirroring, that is, I also want this current to be I naught. Okay, so this voltage also has to be equal to what? V over drive, right? So this voltage also needs to be equal to V over drive. Okay, by the way, one quick question. If I simply leave the circuit like this, no other connection, the way you see it, is this going to work? When I work, do you think there will be mirroring from left to right? So let me simplify it. Let's say I have a circuit which is like this, V naught. Do you think this is going to work? Yes or no? Can't hear. Is going to work? Okay, so do you think, let's say, forget about M1, let me simplify it further. Is this going to work? When I say work, do you think M0 will be biased in saturation? Can you guarantee that it is biased in saturation? No, right? We have gone over this multiple times. So let's say I also put a battery here, VDC. Is this going to work? Can you guarantee saturation? No, right? Again, because two independent sources trying to enforce two different conditions, not going to happen, right? So this structure is not going to work as is. This should be pretty obvious, but I wanted to make it absolutely clear. So which means that I have to find out ways of biasing these two nodes in a way that we ensure that M0, M0A both are in saturation. Okay, fine. So now coming back to the discussion, if we want currents to be mirrored accurately between the left and the right branch, and we focus our attention to the bottom two transistors, M0 and M1. So assuming that the gate to source has been biased in certain way, they are sharing the VGS, not a problem, but we have to ensure that the VDS is also accurate, right? The VDS is also similar, not accurate, also similar. So which means that this voltage has to be equal to, also be equal to V override. Okay, so naturally connecting it like this will not help, because moment I connect it like this, that voltage becomes V overdrive plus one threshold voltage. Okay, so this is not going to help. So I will come back to how to bias this, but before I come back to bias, before I come back here, let's assume somehow we have been able to make it V overdrive. Okay, so what about this voltage? This voltage requirement is now one threshold voltage plus two V overdrive. So let's, for the time being, again assume that we have been able to somehow manufacture this one threshold voltage plus two V overdrive. Okay, so at least M0A and M2 are biased. Let's make that assumption. Now I want to turn my attention back to M0 and M1. Okay, so now let me ask you this. Only think about the stack on the left, I0, M0A and M1. M0 is biased with the way I have shown. I have to generate the gate voltage of M0. Okay, I have to generate the gate voltage of M0 because now currently M0 is, gate is floating. I don't know what voltage you have there. So what will be the strategy? How will you go about thinking about how to generate the gate voltage of M0? And while we are at it, I will I'll urge you to think how we generated the gate voltage of M0 to make sure that the VGS adjusts itself, right? So when we were, if I go back like 10 classes, we were trying to figure out how to ensure that I can bias a transistor using constant current source where the current was getting fed to the drain. And whatever logic we used to ensure that this gets biased properly, I'm going to use the same logic in the circuit in the left, right? So now, if you connect those two, what will be the thought process? So to refresh, let's say let's move our attention to the single transistor circuit on the right. If I want to generate this VGS so that current I0 gets absorbed and the transistor remains in saturation, what was the thought process? What was the argument? What will you observe? What will you tweak? Right. So observe drain voltage, because we are pushing the current into the drain. So if this drain voltage increases, the information that I'm extracting from that observation is that I need to increase the VGS in order to balance the current, right? So if this increases, I need to increase this and vice versa. So the best thing that easiest thing that we could have done was this. And as it turns out, this worked. Okay. So use the same concept in the circuit on the left. Okay. So don't think about this right now. Not necessary to bias M0. Let's say only we are concentrating on the left stack. So same argument. So assuming that the transistors are biased, one question that you should ask directly is who is supposed to set the current in the left stack? I know there is a current source, I0, but if I change this, for example, what I'm essentially saying is if I change this voltage, assuming M0 is biased properly, if I change this voltage, is anything going to happen with regards to transistors going out of saturation? which is the main knob in the left hand side branch? Is it this gate voltage, gate of M naught, or gate of M naught? Gate of M naught, right? So I have some liberty to move around the gate of M naught A, right? Not that critical. So when I am trying to argue how to set the VGS of M naught, I am going to argue in the similar lines as I argued here. Okay. So let's do the same argument. So I'm observing this voltage because I'm pushing the current into that node. If this voltage increases, what is the conclusion? The conclusion is M naught is not biased with sufficient VGS, right? Because it is M naught VGS that is supposed to draw in that current, right? Same argument with whatever we had on the circuit on the right. Just that we have a cascode transistor in between, but the cascode transistor doesn't have any role to play in order to bias the current. So it's almost like invisible with regards to this argument. Okay, so now again, if I not increase, rather if this voltage increases, the information that I am gathering is this current is lower than whatever it is supposed to be, right? So I'm pulling out more current than I am pushing in, which essentially means that the corrective action should be I have to increase the VGS. But whose VGS should I increase? M naught's VGS I should increase, because if this current increases, the VGS of M naught A is automatically going to be set, right? Because the source is going to adjust itself. But in case of M naught, that's not going to happen because source is constantly grounded. Okay, so again, if this voltage increases, the conclusion is I need to increase the VGS of M naught. So again, the same thing. If this voltage increases, I need to increase the gate. If that voltage decreases, I need to decrease the gate. So what is the most obvious conclusion? Obvious solution? Connect directly, right? So I can connect directly. Okay. So now comes the next part to understand whether connecting the circuit like this actually ensures that the transistors are in saturation, right? This is the design part. We came up with synthesis part. We came up with an architecture, but we have to go back and analyze whether whatever logic we put to build this circuit is going to help or not. Okay. So if I connect it like this voltage will be equal to 1 threshold voltage plus V overdrive, right? Assuming threshold voltage and V overdrives are identical for all, if this is like that, can you comment on the minimum voltage here? One V overdrive, right? What about M naught A? What is the VGS of M naught A? One threshold voltage plus V overdrive, that is also good, right? Now, what about the whether M naught A is in saturation or not? Right. So this voltage is that threshold voltage plus V overdrive. That anyway is because M naught is the gate of M naught is connected there. So what about can I comment on if M naught A is in saturation? Assume that V overdrive is less than threshold voltage. I mean that's the assumption that we're anyways taking. So again, I think threshold voltage is, let's say, 500 millivolt. V overdrive is 100 millivolt, right? So then it is right, because what is this voltage? This voltage becomes 500 plus 200, 700, 0.7. What is this voltage? This voltage is 500 plus 100, 0.6. Right? So threshold voltage is 500. So naturally, M naught A is in saturation, no problem. Right? However, now, if I move our attention to the right part of the circuit, this can go to as low as 0.7 minus threshold voltage. right? Which means this can go to 0.2, which is basically 2V overdrive. Okay, and also you must have already observed this voltage and this voltage are of also same. They are also V overdrives, right? So naturally, you see this type of architecture is able to, with this architecture, you are not only able to get all the good things of a cascode, right? The output impedance is high. It's still, since both M1 and M2 are in saturation, you can still get pretty high output impedance. In fact, the same output impedance as with respect to the previous architecture, but it don't have the penalty of having a lot of headroom loss. Right? You can kind of get away with much better, much better headroom. Okay. So this type of architecture, that's why are called wide swing current mirrors. Okay, so by the way, nothing can beat the circuit on the, nothing can beat a single transistor mirror when you come to what is the minimum amount of headroom that you need to leave. It's V overdrive in this case. So you cannot do better than that. But if you have to use a cascode transistor, the minimum you can go is 2V overdrive. So that is something that is obvious, but it's better to make it clear. Okay, fine. So the last part that is remaining here is to figure out how do I get to bias, how do I get to generate this voltage? One threshold voltage plus 2V overdrive, right? Again, I cannot have batteries all the time. And one might argue that I can use a resistive divider, but again, resistive divider has this issue that it will be a fixed voltage again. You don't get to experience the change. If threshold voltage changes, I want that voltage to change also. But if you have a resistive divider circuit, then that's not going to happen. So we need to generate this using, again, transistors, right? So you might have, if you recall, in one of the problem sets, we did this. So this voltage is one threshold voltage plus V overdrive. Right? This is how you generate one threshold voltage plus V overdrive, which is independent of all those stuff that we have been talking about. But now I need to generate one threshold voltage plus 2V overdrive. Right? So again, if I write this VGS is one threshold voltage plus V overdrive, which is, I can write it as now the requirement is I need to generate one threshold voltage plus 2V overdrive, right? So essentially I want this. So can you suggest a way in which I can generate one threshold voltage plus 2V overdrive by tweaking something in this circuit? Right. So if I can simply say that I can take this 2 inside and say that this is right. So essentially, if I go from W by L to W by 4L, right, I'll get one threshold voltage plus 2V overdrive. Right. So that's what is done. So the last piece of puzzle is this voltage is generated okay. So now, again, the way I went about designing this was assuming all these W by Ls are identical, threshold voltage identical and all. But in reality, when you design, you have some freedom. You can change W by L. It's not necessary that threshold voltage has to be identical. You can play around with this, right? But the logic has to be the same. Right? I showed you one particular example, but there can be many others, right? If the same architecture, how do you go about choosing the values of W by L? For example, in the circuit in the left, on this biasing branch, I can as well choose, instead of having W by L to be 1 by 4, I can simply say I am going to increase the I naught by a factor of 4 and keep the same W by L. That is also fine, but you are expending more current. Right? So essentially there are infinite possible solutions for any particular architecture. Just that you have to argue which one you want to choose. Okay. Okay, fine. So now another thing that you should keep in mind is everything that I have shown till now is with an NMOS. You can do the exact same thing using a PMOS transistor. Right? So for example, if I have to use a simple PMOS current mirror, so I am going to essentially say, this is the simplest PMOS current mirror equivalent. Something will be connected here. Similarly, you can put a cascode transistor. Similarly, you can put a cascode transistor here. In the PMOS world, but again, in the PMOS world, you are going to have the same issue because this voltage is one threshold voltage plus 1V overdrive. So which means this voltage and this voltage have to be same if you want accurate mirroring, which means from here to there, you end up having one threshold voltage plus 2V overdrive drop. But if you don't want to expand that drop, then you use the wide swing mirror equivalent of that. Okay, so everything that you can do with PMOS, you can do with NMOS and vice versa. Okay, fine. Any questions about anything till now before we move on from current mirrors? By the way, these are not the only few architectures. You can have like any number of architectures of current mirrors. In fact, you can write a book on that. Right? So, but the logic is essentially the same. Right? So you need to ensure that not only the VGS, the VDS also remains same. And you need to ensure that while not having too much of headroom loss. So all the architectures that you might see later on, if you pursue career in analog circuits, are essentially to ensure these are the few things that are taken. Okay, fine. Anything else on mirrors that you would like to ask me, or any confusion? Okay, if there's nothing, then I would like to leave this topic with this one final thought. We have spent probably 15 minutes describing this in 2 lectures back. So while calculating the VGS from I0, we are neglecting channel and modulation. And that should be obvious, right? I have been using the same old equation when channel and modulation was not introduced. And we could do that simply because it's a compressive nonlinearity with regards to I0 to VGS, not the other way around, right? So you can also do that when you are doing your calculations. Don't get bogged down into, just because the question says consider channel and modulation, doesn't mean that you have to consider it everywhere, right? It's up to you to decide where to consider, where not. Okay. So now essentially we have all the pieces of the puzzle to make a good amplifier. When I say good amplifier, you might be thinking we have been making amplifier since day one, but we still not have a good amplifier because a good one of the characteristics of a good amplifier is its amplification factor should not be dependent on the load that it is driving. Right? So the amplifier, what are the amplifiers that we have seen? We have seen common source amplifier. The gain is GM times RL. It's directly proportional to the load. Right? It's an amplifier which can give you large gain, at least gain more than one, but it's directly proportional to RL. What configuration that we have seen, in which the characteristics is independent of RL? A source follower architecture, a common drain architecture, right? Looking into the source, the impedance is low, right? So we can make a voltage source. The voltage source is supposed to be something whose output impedance is to be much lower than the load that it is driving. But the bad thing about the source follower or a common architecture was you cannot get a gain of more than one. Right? So now the next thing is to marry these two, right? I want gain of more than one, but I want gain independent of R. Right? So in order to do that, whatever we need, we have built up the course till now, right? So now I'm going to use these blocks that we have already found and use them directly to see if we can get there. And if I quickly jog your memory about how we went out to design the common drain amplifier or the source follower amplifier, it was from the logic of negative feedback, right? So let me refresh your memory on negative feedback. I'm sure you are experts in negative feedback now since you are taking 250. So I'm going to take today's class and next class just to briefly go through whatever concepts you are learning there and mold it in a way that we can use it in this course. Okay. So again. So what is the basic premise of negative feedback? A negative feedback is going to work only when you know what you want. Right? And the example that I can give you is, let's say you bought a brand new music device, right? So you or maybe an AirPod or something, and you put it in your ear, and you know that in your head that I want certain volume, which is soothing, right, to my ear. Maybe at the night or the volume might change, but I know what type of volume I want, right? So you turn it on. Can you expect suddenly you will get that magic soothing volume that you want? You will not, right? But it requires some action from your end to ensure that you hit that magic volume. Now, what action you are going to take? You are going to slide that volume bar left or right. Okay, but if we step back and think what you are doing, you are essentially first observing the output. You are essentially first observing the volume that is coming out from the device. And you have an inherent thought that this is good, what level of volume that I am comfortable with. So you are comparing the actual output with an intended output, and you are taking a corrective action by moving the slider left or right. Right? So that's what you are doing. Right? So essentially what we need, so when you have to do a negative feedback loop, right? It can be electrical loop, it can be electromechanical loop, it can be an acoustic loop, doesn't matter. So the thought process is the same. So number one requirement is you need to know what you want. Otherwise, there's nothing anyway you can do in life, right? You need to know what you want. So we need an expected output. Number two, we need to be able to observe the actual output, right? We need to observe an actual output. And number three is I need to take a corrective action based on the difference of the expected and the actual output, right? So need to make a corrective action based on difference of 1 and 2. Okay, so all negative feedback loops in reality work in this simple principle. Okay, the way you ride your cycle, same. The way you walk, same, right? You don't stumble upon every time you walk, even though you are climbing up the stairs or going down a rough terrain. It's because you are doing this, right? The loop is getting completed through your eyes, and the corrective action is the way you are moving your body, right? So if all biochemical loops are also operating in this principle. So just that in this course, we are going to limit ourselves to electronic loops. And for this particular section, we are going to limit ourselves to loops whose controlling variables are all voltages. It can as well be currents. Just that we are going to limit ourselves to voltage control loops. Okay. Okay, fine. So let's say that with that premise, we are going to, the need is to make an amplifier whose gain is more than 1 using negative feedback. Okay. So by the way, I mean, one final thought before I move on, or rather get into this topic. If you design a negative feedback loop using this principle, this will become robust to any ambient change. Because, for example, let's say I take the example of the music player again, right? So for some reason, let's say the player starts to malfunction and you have set it to whatever sweet volume that you want and the volume increased. What are you going to do? You're going to take a corrective action, you are going to decrease the volume, right? So naturally, you are always going to get the output that you want, even though the device slightly malfunctions. If the device completely goes off, then you cannot do anything. But for small changes in ambient conditions or small changes in any condition, you should be able to bring the loop back to wherever it is supposed to be, right? So that's the power of negative feedback loop, right? It is very robust if designed properly. A common source amplifier, for example, is not robust with regards to this, because if the temperature changes, DM changes, the amplification factor changes, right? So in a voltage controlled voltage source, we want a good voltage, good amplifier. We don't want the amplification factor to change. Okay. Okay, fine. So let's get going. So we want, this is a requirement. We want V0 to be equal to some K times Vi, where K is greater than 1. Right? And K is independent of ambient variations. And we want to design it using negative feedback loop, because loops like negative feedback loops are independent of, I mean, their operation is quite beneficial. So if I use these 3 principles, what is the first thing that I am going to see? So let's say I want an expected output. I want to find out what is the expected output. So in this case, what is the expected output? Again, I mean, you have an input Vi. Vi exists. V0 I want. What do I want? K times Vi. So what is the expected output? K times Vi, right? So expected output is K times Vi. So K times Vi is the expected output. What is the actual output? That is V0. Right? So this is I'm observing this, right? This is the output of your music player, you might think. So actual output is V0. So I need to take a corrective action based on the difference, right? So I have to define an error voltage, right? So let's define an error voltage. Let's say I call this VE. Okay. So what corrective action am I going to take? So if V0, let's say, I mean, let's say assume we have made the loop. We haven't put anything, but let's assume we have made the loop and this is going to work. If it's going to work, then what do you expect VE to be? You expect VE to be 0, right? So as a designer, we have to ensure that the circuit is set up in such a way that VE drives to 0, right? Whatever we put between Vi and V0 here should be able to, I should be able to ensure that if V0 is equal to Vi, then VE will be going to 0. And the designer, the thought process is just the inverse of that. If I can ensure VE to be equal to 0, automatically I ensure V0 is equal to KVI. Okay. Okay, fine. So which means that I have to compare V0 with respect to KVI. So I need V0 and I need KVI. Then only I will be able to compare. So do you see a fallacy there? So what I want is generate VE and drive VE to 0. This is the requirement. But in order to generate VE, I need KVI, which I don't have. If I already had, then I wouldn't have bothered, right? So what the alternate is to say that I'll redefine VE. Let me redefine VE. If I redefine VE to be equal to, let's say, V0 over K minus Vi, or Vi minus V0 over K, right? And then I drive it to 0. The result is the same. I will be able to ensure V naught is equal to K di. But now you are going to ask me, how do I generate V naught over T? Criteria is more than one. And note that this K has to be independent of ambient condition variations. Right? Because otherwise I would have actually used the common sense amplifier to generate the factor of K in the first place. But we don't want to do that. So in this case, I want K to be independent of ambient conditions. But is it easier to generate V naught over K than K di? Can you think of a way I can generate V naught over K? Let's say K is 2. Yeah. Voltage divider. Right? So, but what is so good about voltage divider? So let's say I have V naught. I put a voltage divider. Let's say R. So this becomes V naught over 2. And mind you, in an integrated circuit environment, things are placed very tightly next to each other. They are sitting almost at the same place, feeling almost the same temperature, same humidity. Right? So now the temperature changes. Can you comment what will happen to the resistance? It's going to change. I mean, depending on whether the temperature increases or decreases, it's going to change. So this R is going to change by some factor. Right? So I just write it in terms of factors. Depending on the temperature coefficient, it is going to do something. Right? What will happen to this bottom R? It will have the same change. See, both of them have the same change. Individually, they have changed, but the ratio hasn't. Right? So if the ratio hasn't changed, then K hasn't changed. This 2 remains 2. So that's a good thing. Right? So again, when you get into integrated circuit design, you will see that most of the integrated circuit design is to find out what ratios don't change. If I find out what ratios don't change, then I can use that information to make something stable. Right? So if I have to compare something with respect to something which is constant, I need that thing which is constant, right? If everything is changing, then I might as well change with everything, right? So if something is constant, I can, if I can manufacture something that is constant, then I can do some corrective action based on that, right? So here it seems like it is easy to generate that. Not necessarily, right? So let's say this is R1, R2. Okay, so let's say this is R, this is 2R, for example. So this becomes 2 by 3. So in this case, what's going to happen? Do you think that this extra correction factors are going to change? It's not going to change. And if you're not convinced, then I can as well say that I can generate this 2R by putting R's of the same size. Right? So this is another, by simply asking this question, she has hit upon a very important part of IC design, which is not a part of this course, but let me spend a minute on this. The fact that these ratios are not changing is dependent on the fact that these properties of these R's should be identical. The temperature coefficient should be identical. Right? So how do you ensure the temperature coefficients are identical? First, they have to be made of the same material. Otherwise, they are not going to be. Not only that, their dimensions also have to be similar. Because when you are talking about microscopic phenomena, then it depends upon how you have made that resistor. What is the physical dimension of the resistor? If it's longer, wider, thinner, thicker, all those things matter. Right? So essentially, when you want the ratio, you try to make one resistor and you reuse the same dimension resistor and orient them in the same way, and you put them in such a way that you get all identical ones. So almost like making twin siblings. Right? Even though brothers might behave differently, but it's quite possible that twins who have lived together all their life will behave similarly, right? Right? So that's how we generate V naught over K. And in the next lecture, we'll see how do I use this information to build up an exhibitor. Okay.